A lithium metal layer, exactly 28 micrometers thick, contains no active anode material, yet it can hold 5.6 milliamp hours for every square centimeter of its surface. We've spent decades trying to kill the graphite anode because it's dead weight, but when you strip it away, you're left with a battery that has no place to put its ions. To hit 500 watt-hours per kilogram, you have to operate with zero excess lithium, which usually means the battery eats itself in fewer than 80 cycles. The problem is the Solid Electrolyte Interphase, or SEI, a fragile sub-nanometer skin that's supposed to protect the metal, but usually fractures like dry mud. This discovery changes the geometry of the reaction. By forcing the cathode and anode to talk to each other through a crossover-coupled electrolyte called bis-amide-based fluorinated frontier. It starts at the anode, where the NN-dimethyl trifluoroacetamide solvent undergoes reductive defluorination, breaking a CF bond to create a stabilized amide radical, intermediate 1. This radical doesn't just sit there, it swims across the separator to the cathode. At the same time, the lithium difluorooxalate borate salt at the cathode is trying to break down and release carbon dioxide gas. But the arriving intermediate 1 scavenges that breakdown product, effectively sealing the carbon dioxide pathway shut before it can bubble. This produces a second radical, intermediate 2, a boron difluoride, or BF2 fragment, which heads back to the anode.
When this BF2 radical hits the anode, it triggers a spin center shift reaction that weaves the solvent and salt using Multi-TOF mass spectrometry, which times how long laser-blasted fragments take to fly. We know this polymer chain is massive, exceeding 2,000 Daltons. Solid-state nuclear magnetic resonance spectroscopy confirms the chemistry, showing a specific boron to fluorine to hydrogen ratio of 13 to 6 to 1.
This polymer SEI is only 8 nanometers thick, but it's a single-layer amorphous shield. Because it's so uniform, the energy barrier for a lithium-ion to pass through is only 37.4 kilojoules per mole, way lower than the 53.3 kilojoules in previous state-of-the-art electrolytes. This creates planar deposition. As the battery discharges, the lithium doesn't dissolve from the sides or create pits. Instead, the ions leave the top surface synchronously. When the lithium is 100% gone, the SEI doesn't collapse or break. It folds into a self-adaptive mesh film. This mesh creates preferred nucleation sites, so that on the next charge, the lithium grows back exactly where it was. Cryo-FIB-SEM shows the result, a deposit with only 1.6% porosity.
At the cell level, this means we can finally use a lean electrolyte-to-capacity ratio of just 1.5 grams per amp hour. This 2.7 amp hour pouch cell hits a volumetric energy density of 1,668 watt-hours per liter, more than double a standard lithium-ion battery. It even pumps out 2,650 watts per kilogram of power. By eliminating the anode and reaching 100% capacity utilization, we're looking at a 15 to 25% reduction in cost per kilowatt hour. We've proved this works from negative 40 degrees Celsius all the way up to 60 degrees Celsius, and it handles discharge rates up to 7C. We have finally built a high-energy cell that doesn't need a host to stay stable. But it leaves us with one haunting question. If this crossover coupling can stop CO2 and build polymers simultaneously, what other impossible high-voltage chemistries are we currently ignoring?